I was just introduced. My name is Stefanie Milam. I'm at NASA Goddard Space Flight Center. I am the Deputy Project Scientist for Planetary Science on the James Webb Space Telescope. I was actually brought on to the project to make sure that this massive astrophysics mission that's designed to detect the first light of the universe can actually point at the biggest and brightest things in the sky that are flying across very fast. And actually, the brightest thing for JWST to actually even consider is Mars. But we set a lot of requirements based on being able to actually observe Mars, and the good news is we can. So I'm going to give you a little bit about what JWST actually is, and a little bit of highlights of what we are expecting to actually do with Mars science. So the James Webb Space Telescope is a partnership between NASA, ESA, the European Space Agency, and the Canadian Space Agency. It is a mission that's actually being led by NASA Goddard. It is an observatory that our primary contractor is Northrop Grumman. We have 4 science instruments that have been provided by institutions from all over the world, including a near-infrared camera that was provided by the University of Arizona, near-infrared spectrometer provided by the European Space Agency. The mid-infrared instrument was provided by JPL and the European Consortium in the UK, and a fine guidance sensor and near-infrared spectrometer as well, which was provided by the Canadian Space Agency. Operations are going to be done at the Space Telescope Science Institute. This is the same place that does the operations for the Hubble Space Telescope. It's a fully deployable telescope. This is because our primary mirror, let's see if I have a pointer. No pointer. Okay. That's not a pointer. Oh, it is. Okay. The primary mirror is actually 6.5 meters in diameter. This is a massive mirror. And actually, we do not have a rocket that has space available for a payload to actually hold a 6.5 meter diameter telescope. So in order to fit it into a rocket and deploy it in space, we have to actually fold it all the way up so it fits inside the can of an Ariane 5 rocket. It actually operates passively cooled. So basically, we just sit it in the shade from the sun. So the telescope itself is actually cold. It's about 45 degrees Kelvin. This entire sunshade is massive. It's about the size of a tennis court. And it also has to be deployed, obviously. It's 5 layers of a membrane. It's sort of a fancy plastic. You can almost think of it looking like a Mylar balloon or your happy birthday balloons. It's very thin, but it's also very sturdy. This keeps our telescope nice and cold. All the science instruments actually are in this black box that you cannot see in this picture behind the primary mirror. So they're also on the cold side. So we never have much heat actually touching the observatory or the instruments themselves. We're going to be operating at the second Lagrange point. So this is well past the moon. It's a saddle point, stationary point. Lots of observatories have been there. We're actually orbiting the second Lagrange point just to ensure that we're never in the Earth shadow or the moon shadow, but also so we have direct access to the sun, because we do have a small solar panel, which is also on the sunward side, to provide our power, but also so we can have contact with Earth and have direct communication, so data uplink and downlink is accessible a couple times a day. Just to give you some insight about what JWST actually is and where it's come from, its predecessor, in a way, is the Hubble Space Telescope, which is a 2.4 meter diameter telescope that operates at the optical and UV wavelengths primarily, though it does have some near-infrared instruments and has had near-infrared instruments. The Spitzer Space Telescope is a very small, only 0.8 meters, so you can actually almost carry it. And it was sort of a mid-infrared instrument. It's actually still operating as well in a warm mission. So they are still doing some spectroscopy, limited spectroscopy, but more photometry with that instrument today. So JWST kind of fits right in the middle. Of course, it's massive. It's 6.5 meters. But if you look at its sort of collecting area or imaging area, it's almost the same size as Hubble. So we have sort of the direct correlation between the two. James Webb just operates at longer wavelengths. So if you look down here at the wavelength coverage, and that table's probably obscuring all of this, HST is sort of in the optical, UV, and near-infrared. Spitzer is way out here in the mid-infrared. And JWST provides a nice sort of middle ground between the two observatories, but obviously with a lot more collecting area and sensitivity. So it's a general observatory. It isn't going to be doing one type of science. It is available to do science for anybody and anyone in the entire world. There's no proprietary time given to any certain case or person, actually. So it's a 5-year mission minimum, but we're actually carrying fuel to operate for about 10 years, probably longer, depending on how efficiently we can actually operate the observatory. As I said, the primary mirror is 6.5 meters in diameter. That's about 21.3 feet. That's a lot taller than me. And it's a segmented mirror. It's actually comprised of 18 segments. They're beryllium mirrors. They're sort of a bored-out beryllium. They're very, very light, but they're also very, very durable and stable. So as the telescope actually gets hot and cold, the mirrors actually don't flex very much, and we are very confident in their performance. The beryllium is actually gold-plated, so we vapor deposit gold on top of these mirrors. That's because gold is very, very reflective in the near-infrared. It's not that much gold. If you actually condense all the gold for all 18 primary segments down into one solid piece, it's about the size of a golf ball. So you don't want to go try to steal the mirror to make your mom's Mother's Day gift, or it's not that much gold. We do have a 5-layer sun shield, and it's about the size of a tennis court, so it's almost 70 feet long. It's extremely massive, and I have some pictures of some of these things as well. We are at the second Lagrange point, which is almost a million miles away from Earth. As I said, we're operating in the shade of the sun shield, so the operating temperature is below 50 Kelvin. We actually think it's like 40. But we get to say below 50. And as I said, we do have the 4 science instruments. They actually cover wavelengths about 0.6 to 28.5 microns. So you can see around 0.6 microns. It's sort of reddish. But when you get to longer wavelengths, obviously that's well beyond our capabilities. And we're diffraction limited at the lower end. We offer all kinds of different types of capabilities with these instruments, including imaging, spectroscopy, coronagraphy, and aperture mask interferometry, which is going to be spectacular for exoplanets. Since we have this massive sunshade, and we're not sort of in a can to protect the observatory, we are sitting at the second Lagrange point, but it also means the observatory sort of has to sit away from the sun at any given time. And we can't tilt it very much at all, so you have sort of this annulus around the sky that you can see at any given time. So it's like a giant donut that you can see. But the good thing is, as we go around the sun, this annulus actually covers the entire sky a couple times a year. So this is fantastic for us. And but you can also see now why we can't see anything in the inner solar system, because we cannot point towards the sun. So this is why Mars is sort of our limit of opportunity. And in fact, most of the planets, when we observe them, are actually going to be done near quadrature. But this is something we're used to. Planetary scientists always can make do with whatever they're given, and we've done this with other observatories, including Spitzer and the Herschel Space Observatory. So JWST is required to support solar system observations, which is great. And actually, this is something that was sort of supported through the Planetary Science Division as well as Astrophysics Division at headquarters. We can do everything, every planet, Mars on out. We cannot look at Earth. We cannot look at the moon or anything inside of us. But we can look at things even closer, including near-Earth objects, asteroids, and comets. We can track fast-moving things, such as near-Earth objects, asteroids, and comets, up to rates of about 30 milliarc seconds per second. But we think we're going to be able to go a little bit faster. We just kind of need to test that once we get on sky. And this covers just about everything we want to look at. Some of the really fast near-Earth objects, we have to wait until they're a little bit further away and a little slower. but we do very, very well. We have nonlinear tracking, which is basically so anything that has sort of a change in acceleration or has a very eccentric orbit, we can actually follow that very accurately. So I'm going to give you a couple of sensitivity charts. There's going to be a test on this at the end, so I hope you're memorizing them. I just want to give you a sense for how good JWST is with respect to other missions and observatories around the world. So this is basically photometric performance. So if you're considering imaging with JWST in the near infrared to the mid-infrared, JWST is at these two blue lines, and you can see that we're way more sensitive than Spitzer was, especially in the near infrared and lower end of the spectrum. SOFIA is a current airborne observatory, so this is a Boeing 747 that has a big telescope sticking out the side of the airplane. So this is our current access that we actually have to the near infrared and mid infrared, but you can see that we actually really, really do a lot better. And here's Hubble Space Telescope and some ground-based facilities. Spectroscopy, the same thing. So these are the three different spectroscopic instruments for JWST, and you can see, again, we're much, much better than other facilities. Sensitivity is a big thing, which is why doing something like Mars is very, very hard, because we don't care if it's that sensitive. We actually care that we're not going to destroy our instruments by looking at something so bright. But the good news is we can't destroy the instruments, and we won't, and we can do Mars. So this is just lower resolution spectroscopy, just another eye chart. Now here's the test. So these are all the different kinds of modes with the instruments. I just wanted to give you a flavor for sort of all the capabilities, the sort of how much sky we can look at a given time. What you should notice is that the field of view that we can look at any given time is very small. So JWST isn't going to be a surveying instrument, so we're not going to go out and try to find Planet 9, for example. But if we do find Planet 9, we can definitely point at it and go and characterize it and do all the imaging we want. And these are the different spectroscopy modes. JWST has this really cool instrument. It's a multi-object spectrometer. So it's sort of like an array of these tiny little pixels that you can actually open, any one or hundreds at a time. And you can actually look at a star field, and you can get spectra of hundreds of objects at the exact same time. This is the first time this has actually been done in space, so this is really cool. To learn more about anything else in the solar system, I want to point you to, we published a special issue in PASP the beginning of this year. So a lot of the Mars science is actually covered in an article that I'm going to highlight from this particular special issue. So Mars is possible. It is observable with JWST, but it is very challenging because, like I said, it's close and we can't point towards the sun. So we have to wait for Mars to kind of get away from the sun and away from us so we can actually observe it. So this gives us a couple of spans of time where we can actually observe Mars throughout the JWST lifetime. Unfortunately, the next available time for Mars to actually look towards, or the second Lagrange point to look at Mars is the end of 2018. Unfortunately, that's going to be right after we launch, and we will not be ready to observe. So we have to wait until 2020. But that's okay. It gives us more time to prepare and actually beef up our science. As I said, Mars is really fast, but it also gets really slow at times. So this is sort of the rate of motion, and you can see we have these gaps where the rate of motion actually falls into the 30 milliarc second per second. And this also gives you sort of a sense of how big it is whenever we're looking at it. So it's kind of going to be a nice size for us. In fact, if you want to look at how big the instruments are, this is one of our slits for one of our spectrometers. And this is actually a pixel for doing imaging or IFU spectroscopy. So you can see we'll get thousands of pixels across the disk of Mars or multiple slits, so we can do really thorough studies across the entire disk. Well, why do we care about remote science with Mars? You just heard a wonderful talk about orbiters and landers and trying to bring things back, but there's a lot we can actually do and need to do from remote sensing. Basically, you can do global studies, and this is studying how the environment's changing through seasonal variation, day to night, all kinds of other things, and actually try to pinpoint, what's geological activity and how that's influencing the atmosphere, the current atmosphere, the past atmosphere, as well as other effects. So I'm sure you've already heard about water on Mars and the ancient oceans. I think Geronimo Villanueva actually spoke to you a couple days ago. So this is the ancient ocean on Mars that was actually extrapolated based on current D/H measurements that they've made in water. Well, the good news is this is sort of something that we can do with JWST routinely. So this whole work actually took a number of years from ground-based facilities because it's very challenging to do from the ground. JWST has access to these water lines, and it'll be very easy for us to do. And like I said, we'll have lots of pixels across the full disk, and it won't take hardly any time to do these kinds of studies. So we can now start looking into more seasonal variation of this D/H ratio. We can also do maps of methane and other organics. So again, this is something that was actually done from the ground, but also very challenging and takes a lot of time, a lot of ground-based telescope time to do these kinds of studies, whereas JWST will be able to take snapshots effectively of the entire disk at different points in time and actually be able to see how these different organics are cycling through the Martian atmosphere. And yay, organics and more organics. So this is sort of a sense of what we can actually look at, and methane is going to be one of the #1 molecules, because since it's very controversial at times, we know it's there, but it comes and goes, and it's not everywhere. So doing full disk imaging of methane, for example, will be a very significant science return from JWST. But we can also look at all these other guys, including ethane, carbon dioxide, water, and a little bit of these chlorides, for example, if we wanted to study them. Yeah, so that's going to be the great kinds of Mars science, though this isn't all of it. And I encourage you to be creative and think about what you want to do with JWST. So I'll give you a brief status report. I don't know how I'm doing on time. Okay, great. So as of September, actually this is a picture that was taken last month in August, but this is JWST, the observatory with its instruments sitting in our clean room at Goddard Space Flight Center, just down the road. This is a viewing window, so if you ever want to go and see JWST, I recommend you do so, and you do so before next year, because then it's going to leave, and it will leave the public eye until we launch. So you can set up tours, you can go down and you can look at it, and it's fantastic, and you can see that we actually do have an observatory, and I'm not just putting up a bunch of pictures for you. So here it is in all of its glory. So we've had a really busy and successful number of years building up to this point. In fact, everything is sort of coming down to the wire. This year we're putting everything together. So we put the mirrors on the telescope, and we put the instruments on the back of the telescope. And right now we're going through a number of tests at Goddard. Basically, we're going to simulate a launch environment with this massive observatory and make sure everything stays where it's supposed to and doesn't break. Next year, we actually go down and do sort of the same sort of thing, but also in a cryo and vacuum environment. There's a massive test chamber down at Johnson Space Flight Center. And then in 2018, we basically ship it down to French Guiana, where it will launch on the European Space Agency launch pad down there. So again, more pictures, evidence that we have an observatory. This is also one of my favorite pictures, because this is the heart and soul of JWST. These are the science instruments. There are 4, and you can see it's a complete jumbled chaos mess. This is why we do not have a serviceable mission. Well, one of the main reasons. Because basically to get access to any of these 4 science instruments, you have to take everything off in a very systematic way, and it's very complicated, and astronauts with big, thick gloves obviously would have a very hard time trying to do this let alone getting to the second Lagrange point. So yeah, here you go. This is why this is a very complicated instrument. But it is done. They have been successfully tested in Cryovac 3 times. And actually, we have better performance on a lot of our instruments than we even were expecting. So this is really fantastic. This is the massive Cryovac chamber that's actually at Goddard. Here's the little tiny people and the massive instrument package. This was actually completed at the beginning of this year. And we have mirrors, we have optics, beautiful telescope. This is the team after they finished putting everything together, and you can see the NASA logo sort of reflected from the clean room. That was the perspective, if you want to look at it. It's a great publicity picture, and it really is an impressive observatory if you ever have the opportunity. Again, like I said, I encourage you to try to go down to Goddard. One of the most terrifying moments of my life was pointing the telescope down to the ground, exposing the instruments, and dangling them above it, and dropping them down into the back of the telescope. But the good news is they did it, and they did it very well. No hiccups whatsoever. The instruments are now on the back side of the telescope where they belong, and actually everything's being blanketed and covered right now, and ready for the next few tests. We have a sun shield. This is actually a picture of our test sun shield. The flight one is almost finished. But you can see here's all the little people. So if you have Serena Williams and her sister on the other side, this is a massive tennis court, right? With the big telescope right in the middle. Spacecraft bus is complete. It's being built at Northrop Grumman. You can see here's actually the solar panel. Everything is ready to go. Once we do our full cryovac test of the instruments and the optical telescope down at Johnson next year, it will be mounted to the bottom of the observatory with the sun shield. So next year is testing. So this is where we're going to actually do the testing, the cryovac conditions space on the optical telescope and its instruments. This is down at Johnson Space Flight Center. This is Chamber A. If you watch the Armageddon Aerosmith videos, you might recognize it. But it's been completely refurbished since then. And we installed the cryogenic part so that we can actually cool down the entire chamber. And it is extremely massive. So what we do is we have all kinds of test equipment. This is a whole series of different light rays and things like that, so we can actually cool down the telescope and we can make sure we can point and focus the way we want to, and everything works the way it's supposed to. We want to be able to do this remotely, because getting to the second Lagrange point is not something we can do for servicing as we had to do for Hubble. And then, of course, in 2018, we have a full telescope, and it goes to French Kourou, where it's actually going to be folded up. So here's the entire telescope folded up and sitting inside the fairing of an Ariane 5. Not a real picture. So just so you know what's coming up, if you want to know more technical details about JWST, first and foremost, you can contact me, or you can come to some of our other events. If you're going to be at the AAS Division of Planetary Science meeting, we do have workshops and a town hall, and I'm always happy to talk to anybody about this observatory. Where to learn more? Google JWST, or you can go to any of these sites. And thanks for your time.
You showed the very dense instrument package and why it's not serviceable. What about the rest of the vehicle, the mirror, the spacecraft, power, comm, propulsion, etc.? Are there any parts of this that are serviceable?
Nothing is being designed to be serviceable. That's because it will be at the second Lagrange point. So getting out there, you could send a robotic mission out there to do servicing, and that's, so basically we're putting a bullseye on the gas tank in case we want to do so.
NASA is currently designing a system which is, would be capable of reaching with people the second Lagrange point. They don't have anything for it to do, which is why there's a rock around there. But I would imagine they would be delighted to be able to service this as they service the public. I'm just wondering, is there anything here that could be serviced?
Stephanie? May I?
Yeah, go for it.
So there's nothing that can be serviced, and because it's cryogenic, putting a servicing mission near it would damage the mirrors and put deposits on them. So let me just repeat that. There's not only is there nothing that can be serviced, but if you get a servicing mission near it, it will put deposits and obscure the mirrors.
The spacecraft is sunward of the sunscreen.
That's correct, but any servicing mission is going to be outgassing, and the mirrors are a cold trap.
Yeah. Oh, we're running out of time.
For questions, but I'm sure Dr. Milam would be happy to answer them right outside in the hallway.
Yeah, absolutely.